This is video 16. In this video, we use the previous definitions in a more simple example. We also analyze the decomposition of a positive extremum path in extremum arcs. Consider a simple B-infinite window W which is not a cycle. This window is in gray. The graphs G1 and G2 are the cuts of the grid associated to this window. Consider a decomposition of arcs. Here this decomposition is made of 4 positive arcs. Suppose that this decomposition is the decomposition of a path P in extremum arcs in graph G1. Then there exists indices J1 and J2 such that Pj1 and Pj2 are the two extremities of the first arc of the decomposition. Consider similar indices for the others arcs. Suppose that the decomposition is positive. Then since the first arc is positive we have J1 less than J2. Moreover, since the first dual segment is positive then J2 is less than J3. By iterating this reasoning we obtain that J1 is less than J8 and that the path P is positive. Thus if the decomposition is positive then the path P is positive. Now consider the following extremum positive path. Our aim is to show that the decomposition of an extremum positive path is always positive. This is proven in the following videos. Now we apply the definitions of the previous videos on this path. Here are the decomposition of P in extremum arcs in graph 1. This decomposition is the one introduced before. Here are the interiors of the 4 arcs. These interiors are hatched and their windows are in gray. The window W is in white. Here is the window W prime associated to the decomposition. The graphs G3 and G4 are the cut of the grid associated to W prime. Remark that G4 is the union of G2 and of the interiors of the arcs of the decomposition. The graphs G3 is G1 without the interiors of the different arcs. Here is the interior of the first dual segment. This interior is hatched and its window is in gray. The window W is prime is white. Remark that this interior is subgraph of G3. Here is the interior of the second dual segment. Here is the interior of the third dual segment. Here is the window W second associated to the extremum path P. The graphs G5 and G6 are the cut of the grid associated to this window. The graph G5 is obtained by making the union of G3 and the interiors of the finite dual segments. The graph G6 is obtained by removing the interior of the finite dual segments from G4. To summarize, G3 is a subgraph of both G1 and G5 while the graphs G2 and G6 are both subgraph of G4. Now remark that the dual segments are by definition a subgraph of W prime and thus a subgraph of G3. Since G3 is a subgraph of G5 then the dual segments are subgraph of G5. Moreover, a finite dual segment intersect with W second only at its extremities and thus is an elementary arcs of G5. Now we consider the following different areas of the plane. The graph G3 and the interiors of the different dual segments. We remind that G6 is the interior of the dual segment D0 and the dual segment D4. Now consider a path Q which starts in the interior of D1. Suppose that path Q and path P does not intersect. The only way for Q to get out of the interior of D1 is by crossing its window. Since Q and P does not intersect then Q must go through the first dual segment. In this case the path Q enter into the graph G3. Now suppose that the path Q goes through the dual segment E0, then it enters into the interior of the dual segment E0 which is the graph G6. To leave the graph G6, the path Q has to go through the dual segments D0 or the dual segment D4. Here it goes through D4 and it enters in the graph G3 another time. Finally the path Q goes through the dual segment D2 to enter its interior. To summarize, the dual segments delimit different parts of the grid. From the graph G3 any interior can be reached. To enter or to leave an interior, its dual segment must be crossed. From the interior of a dual segment, it is only possible to enter inside the graph G3. Note that the graph G6 has 2 entries, the dual segment D0 and the dual segment D4. As a last remark, the intersections between the path Q and the dual segments create the following arcs of G3. The first one starts in the dual segment D1 and ends in the dual segment D0. The second one starts in D4 and ends in D2. These two segments of the path Q are also arcs of the graph 1. The first one dominates the arc A1, the second one dominates the arcs A3 and A4. Then while moving between the different areas of the grid, the path Q creates arcs of G1 which dominate the arcs of the decomposition. In the following videos we formalize and prove this result for a path which is not extremum. This result is useful to prove that the decomposition of an extremum positive path is always positive and is also useful to prove the jail lemma.